Leveraging the E8 lattice to address decoherence and scale quantum properties to the macroscopic world abstract. This paper explores the theoretical possibility of using the E8 lattice, an exceptionally symmetric higher dimensional structure, to stabilize quantum coherence and prevent decoherence as quantum systems scale up to macroscopic levels. We propose a series of experiments and models that utilize the E8 lattice's unique properties as a scaffolding for encoding and protecting quantum information. By doing so, we aim to create a bridge between the quantum and macroscopic worlds, enabling macroscopic objects to exhibit quantum behavior. The paper outlines the theoretical background, potential experimental designs, and the technological challenges that need to be addressed to interact with the E8 lattice in a meaningful way. Introduction. Background on quantum decoherence. Quantum mechanics governs the behavior of particles at the smallest scales where superposition, entanglement, and other non-classical properties are common. However, as quantum systems interact with their environment, they lose these properties due to decoherence. This transition to classical behavior is one of the key challenges in quantum technologies, particularly in scaling up quantum systems for real-world applications. Zurich, 2003. 1.2. E8 lattice and its role in physics. The E8 lattice is an exceptional Lie group structure that exists in 248 dimensions and has been studied in string theory and high-energy physics as a potential unifying framework for all fundamental forces. Lisi, 2007. Its exceptional symmetry and multidimensional nature suggest it could offer a protective framework for quantum systems, potentially preventing decoherence in large-scale quantum states. Recent experiments have hinted at the manifestation of E8 symmetries in certain condensed matter systems and at quantum critical points. Kodea, etc., 2010. 1.3 Research objective. This paper proposes that by embedding quantum systems in the structure of the E8 lattice, it may be possible to prevent decoherence and preserve quantum properties as systems scale up. The E8 lattice could provide a scaffolding for symmetry-protected quantum states, allowing macroscopic objects to exhibit quantum behavior in our real-world environment. We will outline possible experimental approaches and theoretical models to test this hypothesis. 2. Theoretical framework. 2.1 Decoherence and the quantum classical transition. Decoherence is the process by which a quantum system loses its coherent superposition states through interaction with the environment. The traditional approach to combating decoherence involves isolating the system from its environment using technologies such as cryogenics and vacuum chambers, Zurich, 1991. However, these methods become increasingly difficult as the system scales up in size due to the exponential growth of environmental interactions. 2.2 E8 lattice and symmetry protection. The E8 lattice's exceptional symmetry offers a potential solution to this problem. Symmetry-protected quantum states, like those in topological quantum computing, are robust against local perturbations because their properties are encoded globally in the system's symmetry. The E8 lattice could offer similar protection by embedding quantum information in its higher dimensional structure, shielding it from local environmental interactions that typically lead to decoherence. Lisi 2007, Garrett 2008. 2.3. E8 lattice as a bridge between quantum and classical systems. The hypothesis of this paper is that the E8 lattice can act as a bridge between quantum and classical systems by preserving quantum coherence in larger systems. In this model, the E8 lattice could be seen as a higher dimensional topological structure that holds quantum states in stable configurations, even as they grow in size. By manipulating these states in ways analogous to topological quantum computing, we could theoretically observe macroscopic quantum phenomena. 3. Proposed experiments. 3.1. Experiment 1. Macroscopic superposition using E8 symmetry. Objective: to create a macroscopic superposition state that is protected by the E8 lattice structure. Setup: we propose using a Bose-Einstein condensate, BEC, or a superconducting quantum interference device, SQUID, as a macroscopic quantum system. By embedding the system in an E8 symmetry framework, we hypothesize that the superposition state can be preserved against environmental interactions. Method: this experiment would involve projecting the E8 lattice into a lower dimensional space, e.g. 3D or 4D, and encoding the quantum state of the system within this projection. We would test for macroscopic superposition by observing interference patterns indicative of quantum coherence. Expected outcome: if successful, the E8 lattice should prevent decoherence, allowing the system to maintain superposition at macroscopic scales. 3.2. Experiment 2. E8 protected quantum entanglement at macroscopic scales. Objective: to generate entanglement between two macroscopic systems that is protected by E8 lattice symmetry. Setup: 2. Macroscopic quantum systems, e.g. superconducting circuits, are entangled and embedded in a simulated E8 lattice environment. The lattice's symmetry should protect the entanglement from decoherence. Method: the experiment will measure the persistence of entanglement over time using Bell inequality violations. The role of E8 symmetry in protecting the quantum states will be evaluated by comparing entanglement lifetimes with and without the lattice protection. Expected outcome: enhanced entanglement persistence compared to systems without E8 lattice embedding, demonstrating symmetry, protected entanglement, and a macroscopic scale. 3.3. Experiment 3. Quantum tunneling and E8 symmetry. Objective: to observe quantum tunneling in a macroscopic system using E8 lattice symmetry to stabilize the quantum state. Setup: a macroscopic quantum system such as a Josephson junction is embedded in an E8 lattice structure. This system will be configured to test for quantum tunneling behavior with the hypothesis that the E8 lattice will protect against environmental disturbances that would otherwise lead to decoherence. Method: the experiment will measure the tunneling probability in the macroscopic system and compare it to predictions based on standard quantum mechanical models without symmetry protection. Expected outcome: the E8 lattice should stabilize the quantum tunneling behavior, making it observable at larger scales. 4. Potential impact and challenges. 4.1 Technological challenges. The biggest challenge in implementing these experiments lies in the precise control and manipulation of quantum systems within the E8 lattice framework. creating experimental conditions that allow for projection of the lattice into lower dimensions will require advancements in quantum simulation and material science. Additionally, the isolation of macroscopic quantum systems from environmental noise, even with E8 symmetry protection, remains a significant hurdle. Additionally, the isolation of macroscopic quantum systems from environmental noise, even with E8 symmetry protection, remains a significant hurdle. 4.2. Potential breakthroughs. If successful, these experiments could revolutionize our understanding of the quantum classical transition, offering new ways to control quantum systems at large scales. This could have profound implications for quantum computing, quantum cryptography, and quantum sensors, allowing for macroscopic objects to exhibit quantum behavior in the real world. Conclusion. 5. Conclusion. This paper proposes a novel theoretical and experimental approach to addressing the issue of quantum decoherence at macroscopic scales by leveraging the symmetry of the E8 lattice. By embedding quantum systems within this structure, it may be possible to preserve quantum coherence and observe quantum phenomena in the macroscopic world. While there are significant challenges ahead, the potential rewards, both in terms of fundamental physics and practical quantum technologies, make this a promising direction for future research.